Today we've got Andy Zametzer, who's going to be talking to us about his entire PhD, really. And he's going to be talking to us about lead and the application of lead isotopes to Archean continental crust at various scales. Just now, Thanks, Andy.
Thanks, Hugo. Yeah, we're gathered here today in order to celebrate my PhD. So I'll do some housekeeping first. I'm obviously very grateful to my supervisors for their commitment and open door policy, and for having my back while dealing with a lot of complexity, and for all the long scientific discussions that we had, because I know that my meetings are notoriously long and intense. The sponsors of my PhD are the Geological Survey of Western Australia and Northern Star Resources, so it's an ARC linkage grant. And I would also like to acknowledge the collaborators that are listed here for constant challenges and support in the lab and in the office, but also in the field. And apologies to those who are not on the list. Many people have positively influenced my PhD in one way or another, but thanking them all is beyond the scope of a milestone presentation. This is how an overview of my 5 research chapters looks like. 3 are currently published, the ones flagged green here, and we're also close to publishing the one that is flagged yellow. I color-coded them by the main isotopic tool that was used in these chapters, which is lead isotopes for the first 3 chapters. It's in situ rubidium strontium dating of biotite for chapter number 4, and it's uranium lead geochronology of different minerals for the last chapter. We can also further subdivide these chapters into different themes. The theme for the first 2 chapters would be application of lead isotopes to Archean continental crust of the Yilgarn craton. The theme of chapters 3 and 4 would be timescales and nature of hydrothermal alteration systems, and the theme of the last chapter would be a geochronological window into Paleoarchean crustal evolution. In order to not turn this milestone presentation into a series of lectures, I decided to focus on the lead isotope aspect of this research, which means I'm going to talk about the first 3 chapters. I'm not going to talk about chapter number 4, which is published in Prechem in Research, and I'm also not going to talk about the last chapter, which is currently being prepared for submission upon handing in of my thesis. The common denominator of all of this is decoding the geological history of ancient continental crust and its mineral systems. And what I'm going to do in this presentation is I'll geologically zoom in. I'll talk about some data treatment aspects first. I'll then talk about horizontal spatial patterns of lead isotopes across the Yilgarn craton. After that, I will discuss, or I'll examine how we can use lead isotopes to vertically track geological processes and lead sources through the crust. And eventually, I'll talk about outcrop or even grain scale applications of the lead isotope system. In order to add some spice to this presentation, I decided to incorporate a couple of anonymous reviewer and editor comments, because I think it's quite illustrative how we tackle these comments, how we dealt with them constructively, because a PhD is about enhancing knowledge in a specific field, and enhancing knowledge usually happens through friction and not through harmony. Much more thrilling than the structure of a PhD or the structure of this presentation is the structure of the Earth, which can be described by a dynamic model that would use the mechanical behavior of Earth's materials to subdivide it into the rigid lithosphere, the asthenosphere with higher plasticity, and so on. But we can also use a compositional static model that would use the composition of samples from either the crust or maybe the upper mantle, but it would also use seismic surveys, wave velocities to subdivide the Earth into the crust, the upper mantle, lower mantle, and so on. I've become a man of the crust here at Curtin, so this is what I'm interested in. Crustal evolution through time is a very complicated topic. Many papers have been published on this, and I want to keep this introduction very short. So Hadean protocrust is a contentious topic for itself. If there was felsic crust in the Hadean, then the proportion was rather small. And essentially 2 broad mechanisms have been published to produce felsic continental crust. One would be a magmatic model that involves large-scale differentiation of mafic packages, and a metamorphic model would involve cycles of remelting and recrystallization in order to produce felsic crust. The two models do not necessarily exclude each other, and both do apply to specific periods of time and in specific crustal sections. So there is no real right and wrong here. I'll focus on the Archean and on the Near-Archean between 2.8 and 2.5 GA in particular, which was a period of voluminous crustal growth and cratonization. It was also a very tectonically active period in Earth's history, with a lot of accretion, reaccretion, and rifting of evolved continental blocks. And these conditions set the scene for a lot of hydrothermal fluid flow along zones of crustal weakness. And it has also led to a lot of to the formation of ore deposits through precipitation from these hydrothermal fluids. As I indicated here with the different bar charts, so the amount of felsic continental crust probably grew significantly throughout the Archean. TTG compositions were turned into more potassium-rich granites through increased crustal recycling, and the abundance of sedimentary successions have also become more abundant throughout the Archean. The study area for 4 out of 5 chapters of my PhD is the Yilgarn craton here in Western Australia. The Yilgarn is one of the largest evolved and preserved blocks of ancient lithosphere. Most of its rock units are Near-Archean in age, but it has some older parts as well. The Yilgarn craton is larger than France, I think, so it's a good archive and a good window into the Neo-Archean. I'm using this granites versus greenstones map of the Yilgarn craton in order to highlight the locations of the sample sets that I used for the lead isotope chapters, which is a granite east-west sample transect across the major craton scale Ida fault for chapter 1. It's a sample compilation of published mostly ore lead data, in addition to a couple of granite K-feldspar separates that we analyzed for the first time for chapter 2. And it's a monzogranite target rock sample from the Yarra Baba impact structure for chapter 3. I've already mentioned the Ida fault, which is a major lithospheric boundary in the Yilgarn craton. It separates the older part of the Yilgarn to the west of the fault from the more juvenile Eastern Goldfield superterrane. And all these terrain and domain relationships had initially been established through field relationships mapping, and they got later refined by seismic surveys and also isotopic maps. And classic source tracking tools like lutetium hafnium and samarium neodymium do show a difference across the Ida fault with significantly older model ages to the left on the western side of the Ida fault as compared with more juvenile, younger model ages on the eastern side. Different uranium isotopes, 238 and 235, and the thorium isotope 232 decay to different lead isotopes through time. When dealing with lead isotopes, unlike for uranium-lead geochronology, we're looking for minerals that incorporate lead, but do not incorporate uranium at crystallization. I indicated here that the decay of the 235 uranium isotope to 207 lead is a bit faster because of the shorter half-life of 235 uranium. So we have the source system where the decay happens, and now we have crystallization. And what we want to do is we want to decouple our sampling medium from uranium, from radioactive decay. The classic of lead isotopic investigations is galena. Lead tellurides, lead selenites, lead sulfur salts are also very suitable. Sulfides like pyrite usually have low uranium-lead ratios as well. And the same also goes for K-feldspar. And K-feldspar is particularly interesting in the context of crustal evolution because it's an abundant framework mineral. So these minerals carry a common lead signature. Common lead is any lead incorporated in a mineral at crystallization. And because there's no uranium in, for example, K-feldspar, this common lead signature is not going to change through time. It will reflect the source. This is why it's a suitable source tracking tool. Lead isotopes are usually displayed and normalized in relation to the non-radiogenic lead isotope 204. And this brings me to the various challenges that are involved when we acquire lead isotopic data. And an analytical challenge is the overlap of lead and mercury on mass 204 that needs to be accounted for. And the issue is that with laser ablation analysis, the mercury can sit either in the carrier gas, but it can also sit in the sample itself. One way of doing that is measuring another mercury isotope, for example 2O2, and then use the natural isotopic abundances of mercury isotopes to calculate 2O4 mercury that can then be subtracted from mass 2O4. Editor 1 says, feldspars usually have low uranium-lead ratios, but it cannot be assumed that this ratio is equal to 0. This is feldspar, not galena. There's indeed an issue with ingrowth, and also there's this concept of unsupported radiogenic lead, which is a bit cryptic because there's no real evidence for that. It would describe lead that is not bound in the crystal lattice of K-feldspar, but is precipitated through secondary alteration processes, for example, hydrothermal fluid flow. But everything that precipitates from a fluid would, by definition, probably be an inclusion anyway. So one way or another, we have to deal with the issue of ingrowth in K-feldspar. And in response to this comment, I tried to model the effect that different uranium and lead contents would have on lead isotopic signatures. This is a typical plot of 7,4 versus 6,4 lead with the lead evolution curve, the black curve, and so-called paleogeochrons. Now, paleogeochrons make a prediction about different lead isotopic compositions that we can expect for a specific age according to the model. And I tried to model the different effects that uranium ingrowth would have in combination with different lead contents. Like in this case, I modeled it for 40 ppm lead, which is a typical concentration in K-feldspar. And I also modeled it for 61.2 ppm lead, which is the average concentration of the samples from the Yilgarn granite transect. So these ancient feldspars are a bit more strongly enriched in lead anyway. The key take-home message from this figure is that even with 0.5 ppm uranium, the paleogeochron gets shifted by significant amounts, like almost 200 million years or 150 million years. So 0.5 ppm uranium appears to be a good cutoff grade potentially. Based upon the aforementioned, I have defined filtering criteria that I routinely apply to all my laser ablation granite K-feldspar lead isotopic data. Absolute propagated uncertainty greater than 0.2 for 6,4 and 7,4 ratios and greater than 0.4 for 8,4 ratios is one of these criteria. These numbers are somewhat arbitrary, but my experience tells me that when the absolute propagated uncertainties are in this order of magnitude, then something is off. And then we can always look into we can go back and look into the laser ablation signals. And when we see something like this spiky signal in the center, which is very different as compared to the signal of the spot that was set on clean K-feldspar, then we can say, oh, okay, it looks like we hit something here that was not supposed to be hit, like low lead, perthite lamellae, or possible inclusion. But my filtering criteria would probably catch this data point anyway. What I call explosive removal here is essentially when the laser spot shoots through the K-feldspar and into the epoxy, and that produces a signal that is very striking, and obviously this data point would not be used anyway, because the data, yeah, it's absolutely meaningless. Relative mercury content of more than 5% is something that I routinely apply as a cutoff grade as well, and low lead content, less than 10 ppm, that would usually indicate some sort of secondary process like alteration as well. And as previously mentioned, if the laser ablation configuration allows contemporaneous measurement of the uranium and thorium concentration contemporaneously to lead isotopic analysis, it's advisable to also filter for elevated uranium and thorium concentration. So more than 0.5 ppm would be my recommended cutoff grade. One of the most important derivative parameters of the lead isotope system is mu, which is the uranium-lead ratio. In the source reservoir, omega is the thorium-lead ratio, and kappa describes the relationship between thorium and uranium. Now, Review 1 says, in my opinion, the method of calculating mu values used in this paper is not correct. One should not independently calculate a mu value for 206 and 207 lead by assuming an H. This invalidates the model parameters. For any given model, the 7,4 and 6,4 value define a single mu and a single time. One would think that there's a clear guideline to something as ostensibly fundamental as calculating one of the main derivative parameters of an isotope system. But in the interesting world of lead isotopes, that's not the case. The issue is that we can derive mu from the equations of both uranium-lead decay schemes. And we have to find agreement between these two different appealing equations here somehow in order to calculate one single mu value. The crux is the choice of T2. T2 is the time when the sampling medium gets decoupled from the source reservoir. And one way of doing that is iteratively solving these two equations for lead model age until they agree within some defined level of tolerance. And this is what this reviewer wants us to do. That's a powerful approach in case the age of the sample is not known. But it's also a somewhat circular approach if you know the age of the sample. And it's the model-based perspective. What we do is different. We know the age of the samples because they have been dated or the ages have been well constrained. And we want to use them, or we want to accommodate them as additional geological information in these equations for T2. And another possibility here would be to use source ages, for example, neodymium and hafnium model ages as T2. Now, one thing we wanted to find out was if we can use lead isotopes in an analogous manner to samarium, neodymium, and lutetium hafnium isotopes as a source tracking tool. And in order to do that, we have to calibrate lead evolution curves that describe lead evolution in the Yilgarn craton appropriately. Editor 2, who knows the literature pretty well, says, I'm going back to my point about Overspeed's main finding that plutonic magmas must have experienced multi-stage histories prior to magma generation. That means it was clear in 1975 that the simple whole Earth model of Stacey and Kramer's would fail for the rocks you analyzed. Like, this is specifically referring to an old paper about the Yilgarn craton. So if this has been known ever since the 1970s, it's about time that somebody comes up with new models for the Yilgarn craton. And we can confirm the observation that Stacey and Kramer's model, which is globally the most frequently applied lead evolution model, fails for the Yilgarn. So I plotted all data points from the granite transect in 7.4 versus 6.4 space, together with Stacey and Kramer's model, which is the pink lead evolution curve. And in comparison, I also plotted the new lead evolution model for the bulk silicate earth by Maltese and Metzger that was published in 2020. And in addition to the data points that are here grouped into west of the Ida Fault, the blue data points, and east of the Ida Fault, the orange data points, I also plotted paleogeochrons for the average granite crystallization ages of these data sets. And the simple observation from this plot is that they are offset from the Stacey and Kramer's paleogeochrons by 200 or 150 million years, but they fall almost spot on the Maltese and Metzger paleogeochrons. So even though Maltese and Metzger's model is a single stage lead evolution model, and as we know from the editor comment, this cannot describe the geological reality, it does make the best approximation of lead growth in the Yilgarn craton. And this is what we're looking for. Like, every model is wrong, but we're looking for the best approximation. And our data sets show that we can get this through the Maltese and Metzger framework for the Yilgarn. So with the calibrated lead evolution curves, the short answer is that we can indeed trace a difference across the Ida Fault in mu and also in omega. And that's geologically plausible because what's implied here is higher relative uranium lead and thorium lead ratios west of the Ida Fault, and the more crustal, more strongly recycled, more ancient UNV terrain. And uranium and thorium are lithophile elements and would be expected to fractionate into the crust. So it does make sense that the UNV terrain apparently has higher uranium and higher thorium in relation to a more juvenile Eastern Goldfield superterrain. And the observation is obviously that these results appear to follow the samarium, neodymium, and lutetium hafnium systems. It is not clear whether the subtle difference that we see in the kappa values has any geological meaning, because usually kappa values would be expected to not change much across the continental crust. Even in strongly fractionated granites, the relationship between uranium and thorium wouldn't change much. Both are lithophile, both fractionate to a similar extent. One important thing to clarify is that the differences, or the mu and omega values, are not dependent on the granite crystallization ages. And this is what's shown here. So we have different genetic suites that we were looking at. We have samples with older crystallization ages that have higher mu and omega. And this UNV terrain suite, we have the Eastern Goldfield samples that are relatively close in terms of crystallization ages with lower mu and omega. And then we have these two youngest samples of the transect from the UNV terrain with higher mu and omega. So there's no relationship between granite crystallization ages and mu and omega. This is how the products look like. So we defined new lead evolution curves for the UNME terrain and for the Eastern Goldfield superterrain. The UNME curve is blue, the Eastern Goldfield superterrain curve is orange. And I'm showing this for uranogenic lead space, 7,4 versus 6,4 to the left, and thorogenic lead space, 8,4 versus 6,4 to the right. So we plotted these lead evolution curves by using the Zametzer framework, which is the start date of the model and the initial lead isotope compositions. And the parameters that we have changed are the mu values and omega values, the average values that we calculated for UNME terrain and the Eastern Goldfields. And we're plotting them here in relation to Zametzer's model, which is the black curve that these curves are based on anyway. And we're plotting it in relation to Stacy and Kramer's two-stage model, which is the pink curve. In order to evaluate the differences that these new lead evolution curves make for uranium lead geochronology, we have to talk about common lead correction. So we have some sort of lead signature that gets incorporated at crystallization into a zircon. Zircon is the gold standard when it comes to uranium lead geochronology. Zircon strongly prefers uranium over lead, but there can be a certain amount of common lead in zircon as well. And we have to deal with that because the problem is that uranium will keep decaying on top of this common lead signature in zircon. And we have to subtract this common lead signature somehow in order to calculate a uranium lead age. And this is where lead evolution models can play a role because they can make a prediction about the expected common lead, and they can help us to subtract the common lead signature, and what stands at the end of it is hopefully meaningful uranium lead age. So what is the difference of the new lead evolution curves in relation to Stacy and Kramer's model? I tried to model that for different example sample ages, 1GA, 2GA, 3GA, and for different example common lead contents, here shown on the x-axis in steps of 10% common lead. What is shown on the y-axis is the age delta that is produced in relation to Stacy and Kramer's in million years. So one observation that we can immediately make from this plot is the fact that the differences become increasingly model dependent with high common lead contents, and with old sample ages, with the Archean sample age as well. As we can see for the 3GA example sample age, with high common lead contents, the age delta becomes huge. The inset that is shown here tries to display the difference that it would make for common lead correction with high precision TIMS analyses that can have an uncertainty of only roughly 0.1%. That means the uncertainty of a 1GA analysis would be 1MA. The uncertainty of a 2GA analysis would be 2MA, and so on. And this is shown by these gray bars in the inset. Where the curves intersect the gray bars, this is the minimum common lead content that would be required to make the difference significant for TIMS analysis. And here for old sample ages, for the 3GA curves, it is significant with lower common lead contents greater than 5%. After this little excursion into uranium lead geochronology, I'll circle back to the source tracking aspect of the lead isotope system. And it's interesting to look at the lead isotope derivative parameters in relation to some geochemical parameters. There is a correlation between neodymium lead model ages that we've got for our sample set as well, and uranium and mu and omega. The interesting thing here is that it's a clear relationship. Higher mu and higher omega correlate with older neodymium model ages, and lower mu and lower omega correlate with younger neodymium model ages. So this is another indication, or it's manifest in the data set, that it's probably the initial crust mantle fractionation event that gets preserved, that gets recorded in the lead isotopic data. I also realized that there's a certain relationship, maybe not as strong as the one that is shown in the plot to the left, but there is a certain relationship between median mu and median omega and the geochemical parameter iron number. Iron number is used to classify the differentiation paths of granitic rocks. And it's interesting to see that we have these lower iron number data clusters that correspond with higher omega and higher mu from the UNME terrain, and we have these higher iron number data clusters that correspond with lower mu and lower omega. So even though it might not be statistically robust, this relationship could suggest that granite fractionation in the mid to lower crust is a secondary signal that can also play a role in these lead isotopic data. So there's a handful of publications that document ore lead data, and these ore lead isotopic data in specific ore mineral camps tend to follow neodymium and hafnium signatures in the Yilgarn craton as well. That inspired me to define a lead source concept for the entire Yilgarn craton using different sampling media and subdividing these sampling media into different chemical process groups that would reflect different lead sources through the lithospheric section. In order to do that, I compiled a large lead isotopic database with pretty much everything that has been published previously, in addition to the granite K-feldspar data that we had acquired. So VHMS ores, volcanic hosted massive sulfides, form in extensional settings, but they form at the seafloor, at black smoker-like hydrothermal settings at the seafloor, but nowadays they're trapped as part of the continental crust. So we could expect that they have a relatively close approximation of the mantle signal because of the rapid ascent of melts, of potentially rapid ascent of melts in these extensional settings. And this mantle signature might get mixed with lead of, for example, sediments in the crust. Gold ores are interesting because they form in structurally controlled settings with hydrothermal fluid flow, potentially across a relatively wide range of crustal depths. And there are a number of publications from the 1990s that discuss the possible lead sources of gold ores that could, it is possible that hydrothermal fluids sample a wide range of lead compositions. I've already discussed the possible lead sources of granite K-feldspar, and komatiite-hosted nickel sulfide ores are another chemical process group that also forms in extensional settings. So we could expect them to be similar to the VHMS ores to some extent, but they are related to low lead mafic lithologies, and the ascent of these melts through the continental crust and the thermal erosion that is induced into the continental crust may also lead to contamination with crustal lead isotopic signatures. It would be nice to have a very primitive sampling medium, like geochemically primitive basalts, to get a really close approximation of what the lead signature of the mantle is. And we were relatively hopeful about whole rock primitive basalt data that we've got. The problem is in the way these whole rock lead isotopic data are acquired at the moment, essentially as a byproduct of routine geochemistry in a big facility. We cannot publish them in a peer review process because we cannot exclude the possibility of lead contamination. The way they're crushed and processed in the facility where mining companies would routinely also process or all sorts of ore samples essentially enables the possibility of lead contamination, and there's nothing we can do about that. We would have to process them separately, crush them separately, and then we would maybe be able to use the lead isotopic data of these sample sets. These are again violin plots for the different crustal systems, for the different chemical process groups that I described. We can see that there's a difference in mu and omega in 3 out of 4 systems. The only exception are the gold ores here, which is very interesting because with the wide range of lead sources that we would expect for the gold ores, it's possible that the signatures get blurred, that there is no difference visible because it all gets blurred in the continental crust. Whereas the other ones appear to reflect this initial source signal from potentially the crust mantle fractionation event. Now, what is implied here, or one could read this as uranium, thorium, and lead mass transport in different crustal systems, and an initial source signature that gets preserved in these different crustal subsystems with various crustal modifications. That is the idea that I have in mind, essentially, for the interpretation of this. And one could also argue that the likelihood that this initial source signal is preserved is higher in extensional settings as compared to compressional settings. That would be represented by the gold ores in this particular data set. Editor 2 says contamination. So what is meant here is isotopic contamination in the crust, and hopefully not contamination during sample processing, would go some way towards telescoping a wider original isotope array into a narrower one. So he's referring to the fact that the differences in mu and omega are pretty subtle for most of these groups that I presented. And one way of tackling that is using advanced statistical methods. And I use the Shannon-Weaver Diversity Index, which is a frequent tool that is used in ecology to quantify the diversity of different species in specific habitats. Now, our species here are lead isotope ratios, lead model ages, and also delta T. And I use the Shannon-Weaver Diversity Index. The higher the index, the greater the variability to quantify the variability. And we have some interesting patterns in here. Again, gold ores appear to be the group that have the most diverse lead signatures, which makes sense because, again, potentially the widest variety of lead sources. And we can also see a certain difference across the Isotope when we compare west and east again, that there are, with the exception of gold ores, more diverse signatures in the older, more crustal, more strongly recycled UNV terrain in comparison to more homogeneous lead signatures in the younger, more juvenile Eastern Goldfield superterrane. Linearized lead isotope diagrams following Alberidi and Chateau 1984 are a very interesting alternative and a very different perspective to lead isotopes. So what is plotted here are the individual lead isotope ratios versus these exponential terms. The exponential terms can also simply be converted into a sample age, which is shown to the top of the graphs. The big advantage of these graphs is that we can look at the relative enrichment and depletion of different lead isotopes through time. But we obviously have to at least assume or know the age of the sample. So we're sacrificing the timing aspect that the lead isotope system could give us in order to gain source information. And two key observations from these example plots from one of my publications that I'm showing here are that in the plot to the left, the VHMS ores show a relative depletion of the 207 lead in relation to all the other chemical process groups. And that again is geologically plausible because we would expect them to be potentially the most primitive sampling group or most primitive chemical process group, the closest approximation of the mantle signal. So what is indicated here is that they're showing a relative depletion and they aren't as enriched with crustal lead as the other process groups are. And another observation is that the two plots, the one in the center and the one to the right, show progressive lead enrichment through time in UNV terrain granite cave feldspar samples, but not in the samples from the Eastern Goldfields. So this is indicated by the arrow and by this blob for the Eastern Goldfields. And when you apply a linear regression to these data sets, the progressive lead enrichment through time and the more recycled, more ancient UNV terrain is even statistically robust and again, geologically plausible. We have received very different comments on these linearized lead isotope diagrams as well. Some people argue that the true power of the lead isotope system is the relationship of 207 lead and 206 lead. So we can look at lead isotopes that stem from different uranium lead decay systems, same geochemical pair, but different decay systems. So some people say this is the true power, you should focus on that. That's again the model-based perspective. So we use the 207 lead related temporal information, but it's a bit difficult to get source information this way. And then there are a couple of publications that use these linearized lead isotope diagrams and more strongly focus on the source tracking aspect of the lead isotope system. And one reviewer also encouraged us to use these linearized diagrams even more strongly. This is the source tracking perspective. We use known sample ages to gain source information. But then again, obviously, when we use known sample ages, we cannot gain age information from the lead isotope system. Now, while it looks like these different perspectives are conflicting, the reality is that they simply reflect different applications of the lead isotope system. And we can reach agreement here when we accept the fact that we can make use of both aspects. The transition to the last part of my presentation is that laser spot grids or laser ablation analysis has the big advantage of spatial coverage. What we can do is we can image our granite cave feldspar in detail before, like prior to isotopic analysis, and then we have textual information that we can link to the isotopic information for every individual spot ablation, for every individual analysis. And this is exactly what we have done in the next chapter. I will give a brief introduction to the Yara Baba impact structure first, which is currently the oldest known and preserved terrestrial impact structure. It is located in the northern UNME terrain, and it has been dated by Timmins, Erickson, and others in 2020 at a Paleoproterozoic age, 2 to 29 plus minus 5 MA. We are using a shocked sample from the Monzogranite target rock. That's quite important. So our sample is not from the melt rock, which is the Balangi granophyre, which is shown in purple here on this map with the Paleoproterozoic age. Our sample is from the target rock that has been shocked, but it has not been remelted and recrystallized. The structure had initially been introduced to the literature by Francis MacDonald and others in a 2003 EPSL paper as a deeply eroded impact structure. The field photo that I took last year might be a bit deceiving because it's not a crater that I'm looking into. I'm simply standing on a big outcrop of melt rock. And there is no preserved crater structure or anything. It's probably a deeply eroded structure. One reason why the Yara Baba impact structure was discovered is a big aeromagnetic anomaly, and the original crater diameter has been inferred to be roughly 70 kilometers. Now, what we've done is we have taken a lot of images of shocked K-feldspar from our Yara Baba sample. And in addition to routine BSE imaging, we have acquired EBSD images shown in panels E and F here. E is a so-called relative misorientation map that shows the misorientation angle of the K-feldspar lattice in relation to a point that has been defined as crystalline K-feldspar. F is a so-called band contrast map. Band contrast is essentially a measure of the crystallinity. The brighter the band contrast response, the higher the crystallinity. The darker band contrast, the more heavily damaged the K-feldspar lattice. G is a CL image. CL turned out to be a very sensitive indicator of shock damage in K-feldspar, and H is a lead model H overlay on a band contrast map. Lead model H's are essentially model-based approximations of the granite crystallization age that we can gain from the lead isotope system. Now, two key observations from this are we can document microstructures in the shocked K-feldspar from Yara Baba that have only ever been reported from impact structures. For example, damaged lamellae. We have subplanar and irregular fractures in the K-feldspar. We have broad domains of lattice damage, and we have planar deformation bands with misorientation angles of up to 20 degrees. And another observation here is when we look at the lead model H heat map at this overlay that there's a spatial correlation of microstructures with reset lead isotope signatures. So the older lead model ages that are close to the granite crystallization age of the sample that we know, which is 2650 MA, are usually found in the more highly crystalline, in the more pristine K-feldspar areas, whereas the younger lead model ages correspond with damaged zones, with microstructures in K-feldspar. We try to quantify this relationship by deducing a so-called crystallinity factor through secondary image analysis. So what I've done is I used the spot locations. I produced overlays of my laser spot locations on the band contrast maps. And with a software called ImageJ, I deduced a mean grayscale value of the band contrast image for every individual spot ablation using images like this one. And then I plotted lead model age versus crystallinity factor. And as you can see here, there is a clear correlation. It's even statistically robust for 2 out of 3 grains. Like the R-square value is a bit low for the third grain, but it's generally statistically robust. The higher the crystallinity factor, the older the lead model ages, and the lower the crystallinity factor, the younger the lead model ages. So there is a spatial correlation of damage, microstructures in K-feldspar, and reset lead isotope signatures. Another imaging technique that we apply to the sample is time-of-flight SIMS in order to collect maps of uranium and thorium enrichment in the K-feldspar. So what we see here is a classic BSE image in panel A, a CL image in panel B, and EBSD, relative misorientation and band contrast maps in C and D. And the CL and the EBSD images reveal microstructures that are barely visible to invisible in the BSE image, in this case, damaged anomaly in various orientations. As you can see in the Tofson's map in panel E, we can document uranium and thorium enrichment in K-feldspar that is actually not supposed to be there, but it nicely aligns with the orientation of the microstructures. And then when we take a very close look at a very high magnification, we can identify tiny little micro-inclusions that are shown in panel F. So that's a BSE image with a very high magnification. And they tell us that the uranium and thorium enrichment and these microstructures, at least in places, aligns with monazite and or iron oxide, magnetite or hematite micro-inclusions in many places. This is another example. This is a K-feldspar grain that has a lot of subplanar and irregular fractures. Again, when you look at panel E, the uranium and thorium enrichment nicely corresponds with the orientation of some of these fractures. And in F, the detailed high magnification BSE image shows some iron oxide and some tiny little monazites as well in the dashed area. Now, we have to take a look into the lead isotope systematics of this sample. So I plotted this in relation to the you and me terrain lead evolution curve, the blue lead evolution model that is shown here. And we can, like the laser ablation spots are color-coded by crystallinity factor. Those are the circles shown here in the 7464 diagram. And they are plotted in relation to the granite crystallization age paleogeochron and a paleogeochron with the impact age, 2229 MA. One observation that we can immediately make is that the vast majority of the data plots between these two paleogeochrons. And the kernel density peak lead model age is also in between the two paleogeochrons. It's 2479 MA. So there is some sort of partial to complete rejuvenation and or mixing with an ingrown lead signature going on. And this lead signature, if there's mixing going on, then the lead signature probably records the impact age. We also have this tail of data points that plot to the right towards younger lead model ages that indicate ingrowth. And these data points nicely follow isochron fits, lead-lead isochron fits with the impact age. Those are the sub-horizontal lines that are shown in here. The two triangle symbols symbolize leached and unleached K-feldspar separates that we analyzed using TIMS, so technique, thermal ionization mass spectrometer technique with a very high precision. Those are two separates, and as you can see, both of them also plot in this ingrowth tail, which is very interesting. So leaching the K-feldspar definitely removes some of this impact, some of this ingrowth signature. It shifts the data point to the left, but it's still in the ingrowth tail. So what is implied here is that leaching is better than not leaching, but the full story of what is going on in this shocked K-feldspar will only be gained by setting laser spot grids and sampling a wide range of compositions. Because all the laser data points in relation or in combination with the crystallinity factor will tell us what is really going on. And a question that is brought up is partial ablation of these micro-inclusions that we imaged, for example, the tiny little monocytes that would be expected to contain some thorium and maybe uranium, is that the driver of the isotopic rejuvenation or lead mixing that is evident in the data? That's the evidence that we've got, that's very likely. This is a diagrammatic interpretation of what is going on here. So we have data points that plot close to the crystallization paleogeochron. That's the more pristine lead isotopic signal. We have the data points that plot between the two paleogeochrons. That is some sort of resetting, mixing, rejuvenation signal. And we have this tail of ingrowth that probably reflects ingrowth that happened at the time of the impact. So if we take all of this together, like how can we make sense of the textural and the lead isotopic information? We can tie the sample to a specific pressure range because shock barometry of shock quartz has been conducted on a sample from the same set of outcrops this sample that we're working on was taken from. We can tie it to a specific pressure range. We know that the shock damage structures in there are most likely related to the meteorite impact. And we have tiny little cryptic micro-inclusions that follow these microstructures. We have lead isotope resetting that follows these microstructures. And everything taken together, we need some sort of damage-assisted mass transport of uranium and lead in order to explain what we documented here. And geologically, the most likely explanation is hydrothermal fluid flow on the grain scale. It was probably an impact-induced hydrothermal system that infiltrated the shock damage structures, damaged lamellae, subplanar fractures on the grain scale, and produced what we documented. And such hydrothermal systems are well known from impact structures. For example, from large ones like Chicxulub, but also from structures that are similar in terms of size to the Yara Baba impact structure, and also similar in terms of the target lithology. So monster granite is our target lithology. So that is the most plausible explanation. It's also interesting to think about the fact that what is indicated in our data is uranium mobilization. And in order to mobilize uranium, you would usually expect that you need oxidizing fluids. And the Yara Baba impact structure falls at the end of a period in geological history that is known as the Great Oxidation Event. I looked into some of the recent publications on this topic. Most of these graphs indicate that the atmospheric oxygen content had skyrocketed at roughly 2.2 at the age of the impact. So in a way, one could see our data set as indirect evidence of oxidizing conditions in the Paleoproterozoic. However, we cannot prove that because what we don't know is the current erosional level of the structure. So we cannot prove that the fluids were meteoric. But it's an interesting thing to think about, and an aspect that is worthwhile mentioning. This brings me to the final slide of this presentation, or to the synthesis. It's not easy to summarize everything that I've done in my PhD. I'll try to do this in a as handy way as possible with short statements. For the first chapter, I would say single-stage lead evolution curves can nicely approximate lead evolution in the Yilgarn craton, and there's a correspondence of lead isotopic signatures with spatial patterns of the samarium neodymium and lutetium hafnium isotope systems, classic source tracking tools. That's the horizontal perspective. We can subdivide lead isotopic data from different sampling media into chemical process groups in order to track specific geological processes and lead sources that take place in a continental crust. That is the vertical perspective. And by combining detailed imaging of shock K-feldspar with lead isotopic analysis, we can gain information on cryptic grain-scale hydrothermal alteration in a sample from the Yara Baba impact structure. That's the grain-scale perspective. And I have more editor and review comments in stock. Not all of them are publishable. This is why I decided to conclude this presentation with a couple of iconic images of myself and my principal supervisor while committing crimes in the field. And I hope that this is a nice segue into the discussion.
Fantastic talk, Andy. Good bit of humor too. Anybody have any questions for Andy? If you're online, you can shout out. If you're in the room, just come grab this mic off me. I've got one to lead us in. You're showing you're talking about uranium mobility through maybe oxygenated conditions. But in your lead evolution curves, you've also got thorium mobility. Otherwise, they wouldn't plot along those isochrons.
Yeah.
The thorium is, immobile. It says it's 4+, so it's fluid, immobile. How do you resolve that?
Yeah, very valid question. It's also something that one of the reviewers pointed out. That's obviously one of the more speculative aspects of this research, and the answer is we don't know. Like in a thorogenic lead isotope diagram, the patterns are very similar to what I demonstrated in a uranomgenic plot. So we see the same lead ingrowth tail, but yeah, like it is very hard to impossible to mobilize thorium. So this entire hydrothermal transport idea works well for uranium, but it probably doesn't work for thorium. Like I'm not really familiar of any conditions that would be able to mobilize thorium. Like thorium is known to be pretty much immobile here.
It's a really nice work, Andy. I got a question regarding the lead isotope, the gold ores you showed. On one slide, you showed the Eastern Goldfield and the UAMI has extremely similar lead isotope signatures on the wiring diagram. And then later on, another study showed the lead isotope gold ores are so variable, so indicating multiple sources. So I'm wondering, how you explain the similarity between Eastern Goldfield and the UAMI in terms of lead isotopes of the gold ores. Looks like they have a common lead source across the different terrains.
So what I mean in terms of similarity was the median values of the derivative parameters that we calculated. So when you calculate a median mu, a median relative uranium lead, a median relative thorium lead, and they're very similar, like almost identical for you and me and Eastern Goldfields. What we were trying to do was to quantify the variability of the lead isotope ratios and the variability of lead model ages, and the third parameter was delta T, which is the difference between known sample ages and lead model ages, and we tried to quantify that. And this variability is very high for gold ores in general. Like we have a wide range of lead isotopic compositions for gold ores, but when you calculate derivative parameters and when you calculate median average values of these parameters, then they will be very similar for east and west of the Ida fault. And like a difference that we see in the other sample groups is not evident in the gold ore data. And we explain that by lead mixing, essentially.
But the commodity show strikingly different, derivative parameters across the fault.
This is what I'm saying. Like in the komatiate-hosted nickel sulfide ores and in the VHMS ores and in the granite K feldspar, there is this source signal that is probably related to crust mantle fractionation that gets preserved. And the source signal used to be in the gold ores as well, probably, but it's not visible any longer because it got blurred through all sorts of crustal processes, through all sorts of secondary processes. That's the idea of this entire concept of this big Yilgarn lead database. We have this initial source-related lead isotopic signature, and it is preserved in different groups that represent different crustal systems with various modifications. And in the case of the gold ores, the modification is so big that it would blur the difference across the Ida fault. It's not visible any longer.